Welcome back, everyone, to another Forge College Explainer. Seriously, think of today's session as a gritty, hands-on engineering workshop where we're getting right under the hood of Solana smart contracts. If you've been tracking with us in the Programming with Solana track, you know we laid some heavy groundwork in our last lesson integrating Borsh into Solana data structures. We figured out how to actually get our data on-chain using Borsh. But today we are taking it to the absolute next level. We aren't just trying to make it work anymore. We're going to make it lean, mean, and incredibly efficient. So let's just dive right into optimizing our data layouts. All right, here is our blueprint for today. We're going to hit 5 key things. First, the actual cost of data bloat. Second, the struct makeover. Third, measuring our footprint. Fourth, round-trip stress testing. And finally, tying it all together with CI checks. Let's get into it. Section 1. The cost of data bloat. Let's talk about why every single byte actually matters. Now, you might be sitting there wondering, why on earth are we going through all this trouble just to save a tiny handful of bytes? Well, on Solana, space is quite literally money. Basically, we are about to play Marie Kondo for smart contracts. We're going to look at our Rust structs, find that wasted space, and ask if those bytes spark joy. And spoiler alert, if they don't, we are tossing them out. To really get this, we've got to look at how different data types eat up space. Think of fixed-sized primitives, like a standard U64 integer, as rigid, perfectly predictable heavy-moving boxes. You always know exactly how much room they're going to take up. But then, we have variable-length fields, like a string or a vec. These are way more like squishy, totally unpredictable bags of clothes. Because Borsh needs to know how big these bags are before it opens them up, it encodes a length prefix right before the actual bytes. And that prefix, it takes up extra room. When you carelessly just chuck squishy bags and rigid boxes into the same storage unit, you get awkward gaps, you get alignment padding, and you get wasted space. And every single extra wasted byte jacks up your on-chain rent and your RPC bandwidth. Believe me, it adds up incredibly fast. Moving right along to Section 2, the struct makeover. Time to talk packing efficiency. So how do we actually fix this data bloat? Well, you have to follow the absolute, immutable, golden rule of structural engineering in Rust. Here it is. Group fixed-size primitives together and place variable-length fields at the end. Seriously, by keeping all your perfectly predictable heavy boxes bunched together and shoving all the unpredictable squishy bags to the back of the closet, you drastically reduce that alignment padding and stop those length prefixes from clustering awkwardly between your integers. Let's see this rule in action, shall we? Take a look at a naive account layout. It recklessly interleaves a U64 ID, then a string name, then another U64 counter, and finally a vec of tags. Honestly, it's an absolute packing disaster. It's boxes, bags, just a mess. But when we optimize it, it becomes a total thing of beauty. We just group that U64 ID and the U64 counter right at the top. Boom, the heavy boxes are packed first. Then we place the string and the vec neatly at the very end. Notice, we haven't actually changed the data we're storing at all. Not one bit. We just completely changed the blueprint of how it's organized. Which brings us to Section 3, measuring the footprint. Let's calculate our actual savings. Okay, so now that we have our newly engineered blueprints, we need the cold hard data. When we serialize the exact same sample data using both of those layouts we just talked about, the payoff is actually dramatic. The naive account weighs in at 78 bytes, but our optimized version, just 70 bytes. Literally just reorganizing the fields shaved off 8 bytes of structural overhead. Now, I know what you're thinking. 8 bytes might not sound like a whole lot to a traditional web developer, but multiply those 8 bytes across thousands or even millions of user accounts on Solana. Yeah, you're looking at massive, massive savings in rent and bandwidth. To actually get those numbers, we built a super simple profiler binary. Let's walk through the steps real quick. Step 1, generate a deterministic sample. Guys, this is incredibly important. You absolutely must use fixed constants like the number 42 or the exact string example, rather than random IDs or timestamps. If your data changes every single time you run the test, your measurements are completely useless. Step 2, we serialize that sample into bytes using the try-to-vec function provided by Borsh. And finally, step 3, we simply measure the length of that resulting vector. It's highly reproducible, and it tells us exactly what our on-chain footprint is going to be. All right, Section 4, round-trip stress testing. We've got to ensure correctness. Listen, an optimized struct is completely 100% useless if it corrupts your data. We need to put our sleek new layout through a serious quality assurance wind tunnel. And a round-trip test is exactly what it sounds like. We serialize our data structure into bytes, and then we immediately deserialize it using try from slice to pull that data right back out. The goal here is to make absolutely sure the final output matches our original input perfectly. We're basically checking to ensure the serialization process didn't secretly pack on some extra bytes, drop a field entirely, or just scramble our strings while we weren't looking. And the best part? In Rust, this is beautifully simple to check. We just use the assert_ macro. We assert that our original optimized sample is exactly equal to the data we just deserialized back from those bytes. These simple assertions act as an immediate stress test. They instantly flag any serialization bugs, weird type mismatches, or layout errors way before they ever make it near the live blockchain. And finally, Section 5, CI checks and next steps. Time to set up our automated guards. So, we've cleaned up the struct, we've measured the sweet savings, and we've verified the data. Now we have to set up automated guards to make sure that data bloat never ever returns. To do this, we establish a strict baseline threshold. Let's say 40 bytes for a specific small account layout. We then coke our test scripts so that if some future contributor accidentally adds a redundant field, or maybe they just plop a squishy string right in the middle of our perfectly grouped integers and push the size above that 40-byte baseline, the test will intentionally fail. It spits out a non-zero exit code. This basically acts as a ruthless automated bouncer at the door of your repository, flat out rejecting any code that tries to introduce data bloat. All right, let's bring it all together and summarize the 3 huge takeaways from today's explainer. First off, always group your fixed size primitives first and leave your variable length fields for last. Second, when you are measuring, stabilize your test samples with fixed constants so your metrics are actually reflecting the layout and not just random payload variations. And third, bake these size and round-trip regression checks directly into your continuous integration pipeline. Seriously, automated tests are the ultimate bouncers against bloated account sizes. We've successfully optimized our Borsh serialization today. We're saving money, we're saving space, but I want to leave you with this somewhat provocative question to chew on. Your data is compact, yes, but is it actually secure? What happens when someone intentionally sends us maliciously crafted bytes? Well, that exact malicious attack vector is what we're going to tackle in our very next lesson on security and validation. Thank you so much for hanging out with me in this Forge College Explainer. If you want to learn how to guard these newly compact structs of yours, or you just want to continue your broader Web3 journey, be sure to visit forge.college. Keep building, stay secure, and I will catch you in the next explainer.